Hi, welcome. My name is Mitchell Chandler, and thanks for your interest in my poster. So in this work, I combine sustained ocean observations from HIXBT transects, satellite altimetry, Argo profiles, and Argo subsurface trajectories to produce monthly resolution estimates of cross-transect absolute geostrophic velocity between the surface and almost 2,000 meters depth over the period 2004 through to 2019. This method is applied to HRXBT transects crossing the subtropical western boundary currents of the Indian and Pacific Oceans. So that's the Agulhas Current, the East Australian Current, and the Kuroshio. These velocity time series are longer than is typically feasible from subsurface observations in these western boundary currents. And additionally, the use of globally available observations means that the method could also be applied in other boundary current regions. More information on the methodology can be found in our paper linked to here. So using the 16-year geostrophic velocity time series, I computed cross-transect transport. This transport is of just the poleward flowing western boundary current, and so it ignores any potential recirculation features that may be present. Using these transport time series, I observed a significant decrease in transport in the Kuroshio, which was contributed to by both a decrease in current speed and a decrease in current width. In comparison, no significant change in transport was observed in the East Australian Current or the Agulhas Current. So in the East Australian Current, this may be due to competing influences of an increase in current speed, but a decrease in current width. While in the Agulhas Current, there was no significant change in current speed, but an increase in current width was observed. These 16-year time series also provide robust estimates of the seasonality in these western boundary currents. All three western boundary currents demonstrated remarkably similar transport seasonal cycles, with poleward transport stronger in the summer and weaker in the winter. These transport seasonal cycles appear to be driven more by changes in the speed of each western boundary current rather than by changes in the width. And although an examination of forcing mechanisms was not part of the current study, others have suggested that local wind stress is important in driving the seasonal cycle in certain western boundary currents. Given the similarities in the transport seasonal cycles here, I'm hypothesizing that similar forcing mechanisms are acting in each of these three western boundary currents. To find out more about this study, I encourage you to check out our paper, which has been published in GRL, or feel free to contact me via email or through my socials, which can be found on my website. Once again, thanks for your interest in my poster and my work.